Hello guys, welcome to another video of consistent hashing. In this video, we will talk about how a consistent hashing is implemented in a real world. In real world, consistent hashing is implemented by many different types of data structures. So we will start with the simplest one, which is an array. So to implement consistent hashing using an array, you can just take the hash of all the servers that are present and active, and you can just maintain an array of all those hash with the server info in a sorted manner of hash. So let's say we have three servers whose hash are 15, 40, 70. We can just maintain an array of these three elements. Now, when you want to map a key to a server, then you can do something like this. Let's say we have a key and its hash came to be like 35. Now we just need to, if you will just imagine, if you have a ring, and if you will move in clockwise direction, whatever server will come will be encountered first will be having the hash greater than or equal to that key's hash, right? So same thing we will apply in the array. So when we calculate our key hash, which is let's say 35, we will just look for an element. We will just look for an hash that is greater than or equal to that key's hash. So in this array is pretty small, so you can just say, just see that that server is this 40, which is the middle one, right? But in case an array is big, you can use we generally use binary search to get the server which needs to be mapped with that particular key. So you can see the complexity here for mapping a key to a server node is log n, because binary search complexity is log n. But adding a new server or removing a server is not easy, because let's say you are adding a new server. Let's say the hash of that server is 10. Then you need to add that server in the beginning of this array, right? Before 15 at index 0, right? So you need to move all these elements to the right, one index to the right, right? So it will take you n complexity, big O n complexity, because you will be moving most of the elements by one index or maybe more than one index in case of virtual nodes. So the complexity of adding or removing a server is not log n, it will be big O of n. Hence it's not that efficient. So it's not used in big scales, big systems where the servers are in thousands and we have many virtual nodes. It's only used in small scale applications. For big applications, we generally use BSTs, which is balanced search trees, like AVL tree, red black tree, or spray trees are also there. Or we use, if in case you are using Java or maybe C++ or any other library which has its own collection, then we use a map which is already implemented in these libraries. For example, Java has map as a collection, right? And C++ has map in STL. So we can use those. As map generally uses BST as their implementation, the complexity in both the cases will be same. It's just that if you will create your own BST, then you just have to deal with the complexity of creating and managing that BST as well. So as the complexity in both of these are same, I will be just going through the process of where we create our own BST using AVL tree. I will be taking an example of AVL tree to understand the process of adding a node or removing a server node in consistent hashing. So let's say we have three servers initially with the hashes 15, 40 and 70. I've just put some random values here for hashes. When you will insert these three in a AVL tree, it will look something like this. 40 will be the root node and 50 and 70 will be the children. How a AVL tree self-balance itself, I can create another video on that if you want. That is a huge topic, so we will cover that in another video. But AVL tree will never get skewed. For example, something like this will never happen. Like 40 will be the root, then the right child will be 70, then the right child it will have another right child maybe 80, then another right child 90. So it will not go in one direction, it will always balance itself. It will try to be a complete binary tree as much as possible. So as now let's say this is our initial tree. Now if we are adding a new node. Let's say we have a new server node with the hash value of 50, and when we try to add it to this particular AVL tree, the tree will look something like this. So it will start with the root node 40. As it is greater, it will go to the right. Now 70 will be there. At the 50 value is smaller than 70, it will go to the left. So left is null, right? So 50 will become the left child of node 70. And similarly you can keep on inserting here, and as you can see the nodes that are traversed while inserting a new node uh, depends on the height of the tree, and height of a AVL or any BST self-balance BST is log n. So the complexity of adding a node is log n. Similarly, complexity of removing a node from a self-balanced search tree is log n, because when you remove a node, you just need to traverse the path from that root to the particular node. For example, here again, if we are removing the node 50, we just need to find out where 50 is, and that nodes that will be traversed in finding the node 50 will be the nodes that belongs to the path from root to that node, which again depends on the height of the tree, right? And as height of the tree cannot be more than log n, so the time complexity for removing a node as well is log n. I can create a separate video on all the operations of AVL tree, how the rotation happens and how it self balances itself. But for now, you can just say the complexity of adding or removing a node from an AVL tree is log n. Similarly, when you want to map a key, for example, let's say we are taking an example of a key, let's say 65. Let's say there is a key whose hash is 65. Now we want to map it to a server. So to map it to a server, we will just look for a node in AVL tree whose hash is greater than or equal to the key's hash, which is 60. So in this example, as you can see, the node which is whose hash is greater than or equal to the key's hash, which is 60 is 70. So we will just map that key to this particular server node. Again, to find such a node will take log n complexity, because you just have to use BST properties and either move left or right depending on your hash is greater than or less than to this particular node. So if let's take the example, let's say we are doing it for 60. Now 60 is greater than 40, so we will move to the right. Now we will see 60 is less than 70, so we will go to the left of the 70 node. Now we see 50 is smaller, and 50 doesn't have any right children, right? So we know the node that is present in this AVL tree which is greater than or equal to the value 60 is the 70 only. So we will just map that key to this particular node. And again, it took us log n time to find such a server, because we are just traversing the height of the tree once, same as we do for adding a node or for removing a server node. So the complexity in all the operations when we use a self-balanced search tree to implement consistent hashing is log n. Now let's review the complexity here. I have just created a table with all the complexities and that will be there on doing an operation in AVL tree for consistent hashing. So while adding a node or removing a node, apart from finding that particular node which takes log n time, you will be redistributing some keys, right? Because when you add a node, or when there is a server failure and you remove the nodes from consistent hashing, whatever keys that belong to that server which failed will get redistributed to other servers. Or when you add a node, whatever keys that belong to the left of that server hash will get redistributed to that particular server, right? So as we know, in consistent hashing, maximum number of keys that will be distributed will be k by n, which is k is equal to total number of keys and n is total number of servers. So at max, k by n keys will be redistributed. Hence the complexity in adding a node and removing a node will become k by n plus log n. We go of k by n plus log n. K by n for distributing the keys and log n for retraversal to add or remove a server. But mapping or removing a key is easy. You will just have to traverse the tree once and you can just add or remove a key in log n time. Now in this example, as we are seeing, we are just storing the info of node servers in the key. We are just creating a tree based on the hash values and we just store the server info in the tree, right? So where are the keys stored? Like how do we know what keys we need to redistribute when a server is added or when a server fails, right? Because we don't have any info about the keys in this particular tree, right? So let's go to that. So keys along with their values are stored in the server node because we don't uh, have any significant of them in consistent hashing. Consistent hashing is just to redirect a particular request or redirect a particular key on a server in a balanced manner so that the load on our servers remains balanced, right? So keys are actually stored in the server itself on which they are getting mapped to. They do not hold any data. Consistent hashing does not hold any data about keys. So if they are not stored in AVL, how do we know which ones to reassign if the server fails, right? So there are different ways that are used in the real world scenarios for that. So some of them, let's say on the fly lookup actually. On the fly lookup means, um, let's say the keys are remapped by clients itself. For example, let's say one of the requests came and it got mapped to server A, and let's say server A fails. Now another request come from the client, then it will get mapped to server B. It will get remapped to server B because as soon as the server A fails, it will be deleted from the AVL, right? So when a new request will come from the same client, a new lookup will happen, and the key will be remapped to another server which is active. So this is called on the fly lookup, where a client only redistribute the key based on the updated AVL tree. It happens in Netflix EV Cache or DynamoDB. Some examples which use this approach I have written here. Other other approach is rebalancing tool. Like you have some external tool that does the job for you. So when a server gets added or when a server is removed from your consistent hashing ring, then this tool is responsible for finding out what ranges were present in that particular server or what ranges it needs to be remapped when a server is added or if a failure happens, and what neighboring nodes will receive them, and it will move the data according to the new tree. Whenever a server fails or added to the hash ring, then it does the job of rebalancing all the keys. But for it to find out what keys are there to redistribute, there are different strategies again used to get the data of the keys. So let's understand the problem first. Even if we are using a rebalancing tool, let's say one of our key was stored on server B, and let's say server B crashes. We know the keys that belongs to the previous node hash and the B's hash are affected. The server that is present before B hash and that the B hash, between those range, whatever keys are present, they will be affected, right? They needs to be redistributed. But we don't know what are these keys. Like we know the range because we have the previous server hash as well as the hash of the server which failed, right? We know the range. The keys which belongs to this range will be redistributed, but we don't know the keys values itself, right? So for that there are some strategies used. So, a simple strategy is replication. Like we replicate the key data on multiple servers. So let's say there is a key user 123 which a hash of 47. Let's say it was mapped to server B, but we make a replica of it in server C and server A as well. So if B fails, server A or server C will still have data, and our tool can use that data to redistribute the keys again, and actually update the data as well. Another approach is something like which is used in memcache. It's similar to this approach on the fly lookup. So here memcache, uh, as you I'm not, if you're aware, memcache is a tool that is used for caching, in memory caching, or you can create a caching server itself. But memcache uh, does not replicate any caching key. So for example, let's say you are running different servers of the memcache, and each server has some data. For example, let's say you have 100 rows in your DB, and let's say 10 servers of memcache are running, and each server has 10 rows of data cached into them. So let's say one of the server fails, then all the cache that belongs to that particular server will get lost. But that is not a big problem for us because only a small amount of caching is affected, right? Because 90% of data is still cached. So you will be not receiving a lot of cache misses. You will be receiving only a small amount of cache miss, and whenever a new request will come, which belongs to that cache miss part, it will just go to the DB. It will get the fresh data. It will again cache it to some another server. So the redistributing will happen automatically. The cache will rebuild on its own, through lazy loading. Whenever the request will come, it will get the keys will distribute automatically, and the lazy with this approach the cache will rebuild again. Uh, so similarly, when the server will come up, again the same thing will happen, because let's say server A come up again. Now it doesn't have any cache, but again when the new request will come, it will again go back to server A because the server A was down, right? So let's say it got redistributed to server B. Now server A is back again. Now again with this lazy loading thing, whenever the request will come, it will again go to server A. There will be a cache miss. It will go to DB and it will update the data in server A, and same thing will happen, right? So there is no much effect on the system because number of cache misses are very small in this particular case. So uh, and there is no permanent data loss as well because you have your DB as a source of truth, right? So it's a simple strategy which is used in caching techniques like memcache and EV cache. But if you don't have any replication like this, as in this first example, or any external source of truth like a DB in case of caching, then there is no way to find out which keys needs to be redistributed, and your data will be lost. So let's quickly move to advantages and some drawbacks of consistent hashing. Obviously, consistent hashing helps in horizontal scaling because as soon as the server scales up, it gets added to the ring and the load balances itself. And it minimizes the data movement as well. So number of keys that needs to be redistributed are minimized. So as we have seen in the example above, with the static hashing, number of keys that needs to be distributed are much larger than the keys in consistent hashing. So these are the basic advantages of consistent hashing. Other advantages with virtual nodes are like if you the more number of virtual nodes, normally with large number of virtual nodes, the distribution will be uniform among all the nodes. Uh, in both the cases, whenever you add a new server, you add the virtual nodes as well for that server, right? So in both the cases, if a server goes down or a server comes up, the load that the load will be distributed uniformly on the all other servers, right? So this is one of the advantage of virtual node. Drawbacks are simple because consistent hashing always map a request or a key to a particular server only. It will always, so it's basically maintaining a session on a server, right? So let's say a object become popular, so a key become popular, and it's receiving a many request. It's receiving, let's say, 40% of the traffic is about that key only, then your 40% of traffic will go to the same server because in consistent hashing, a key is always mapped to the same server until unless the server goes down. This is one of the drawback of consistent hashing. Always, also there are cost on memory and the complexity that needs to be handled while maintaining your BST. So this is some extra costs you need to take care of. Replication of data objects is also challenging because replicating data in multiple nodes and retrieving it from it while redistributing the key is also a challenging thing. Also, virtual nodes might need some tuning. When you are using virtual nodes, you need to do some experiment and tune them, that the number of nodes which are suitable for your scenario. Let's quickly go into the applications of consistent hashing. Uh, as we know, they are used in key value stores by Amazon DynamoDB. So Amazon DynamoDB has a partition key. Like the key is hashed using consistent hash function, which can be MD5 or SH256, and it partitions its data across multiple nodes. So it creates a multiple nodes, and it partitions its stored data into these many nodes using consistent hashing. And if a node goes down, only a small number of keys are reassigned to the nodes. So it's easy to balance the node here. Similarly, for Apache Cassandra, which is a column-based store, it uses consistent hashing to maintain its load and move its data from one range to another. It uses a similar process as Amazon DynamoDB. Like it, when a new node is added, it will just calculate the range which needs to be redistributed, and it will just redistribute those keys only. Similarly, Akamai CDN systems and GitHub Load Balancer also uses them. So GitHub Load Balancer uses them for session stickiness, like for a user session, for a user request to go to always go to the same server. Like for sticky sessions, it generally uses it. And Akamai CDN systems they use for mapping content on different nodes and balancing the load there. And also distributing the data again when a node goes offline. So these are all the applications and advantages and disadvantages of consistent hashing. Let's move into the demo real quickly. So for demo purpose, I have created a server using Node.js, and in this I have created these APIs. So server API, post server API is used to add a server. Delete API is used to delete a server. This keys API used to add a key on the consistent hashing ring, and this state API just returns the state of the ring to the front end, and front end um, displays it on the screen. So we will go into the front end part later. Let's understand what I have done in this backend part of the code. So if I go inside this adding a server, you can see by default I have kept the virtual node count to 3. For demo purpose I have kept it small, but this can be huge. So I'm just I have created two nodes here. One is server node, which contains all the virtual nodes that belongs to it, and an ID, a unique ID to this particular server. And in virtual node, it will have the hash value for this particular vnode, and the server it belongs to, the actual server this particular virtual node belongs to. So if you will go back here, you can see I'm just creating a server, and for this server I'm creating 3 virtual nodes and inserting each virtual node in the hash ring. Also for each virtual node I'm adding this server as a reference, because this virtual node belongs to this particular server, right? So just to map it, I'm just adding a server here as well. So if you will go into this insert operation, this is basically an AVL tree operation. So I'm using AVL tree for this demo. So if you go to the insert, this is just a simple AVL tree insert operation where we just add it like a binary search tree, and then we just rotate based on some conditions. I will talk about this in detail in a separate video. So for now, just remember it's a simple binary search tree insertion in AVL tree. Similarly, when you try to delete a node, let's say when you try to remove a server, we get the server ID in the request, and for all the virtual nodes that belongs to the server, for example, I'm finding the server this server ID belongs to, and all the virtual nodes that belongs to the server, I'm just removing all of them from the tree, because if server is down, then all its virtual nodes as should be removed from the ring, right? Because no traffic can be redirected to this server anymore. So for all the virtual nodes, I'm just deleting it from the AVL tree. So here again, this is just the delete operation on AVL tree. This I will explain in another video. And okay, and the last API which we have here, state, it just returns the um, state of the whole ring to the UI. So let's go to the UI. I've already started the server and the UI. Let me refresh it. So in this UI I've just added a small form where I can add a server, remove a server, or add a key on the consistent hashing ring. So let me just add a server A. So as you can see, I'm adding 3 virtual nodes for a particular server, right? So we are seeing 3 nodes here with server A, and as you can see, their hashes are different. So I'm printing the name of the server as well as their hashes, so that it will be easy for us to know how this is working. So let me add one more server. Let me add one more. See. So you can see as I'm adding new servers, the tree is balancing itself, right? So as you can see, it's not getting skewed to one side. It's moving nodes from here and there, and it's balancing itself. So this is how self-balancing trees work. Now let's try to add a key here. I'll just use key 1. I'll just keep on adding multiple keys so that there are keys on each server. Let's say I'll just add key 5 and key 6. Okay, so you can see the key 1 is mapped to server C, key 2 is mapped to server A, 3 and 4 are mapped to server C, and 5 and 6 to server B. If you will compare the hashes here, right? So let's take example of this key 5. So you can see here the hash of this key 5 is very small. Like if you will compare it with all the hashes that are present in this tree for all the nodes, it's smaller than all of them, right? So if so there is a or so it will just go to the left part of the tree, right? Let's take the example. This hash is smaller than this particular hash, it will go to the left. It's again smaller to this hash, it will go to the left. It's again smaller, as the left is null, so this is our node, right? So it got mapped to server B. Similarly, if a hash is greater than all the hash that are present in this tree, for example, let's say we have a hash something like 99999, which is like greater than all of these hashes, right? So it will be greater than this, it will be greater than this. We will move right, we again move right, and we again move right. So now this is a null pointer, right? So we couldn't find any node which is present in this tree for which the hash is greater than or equal to this particular hash, which is like 3999. Actually there is a hash present like this. So this hash, key 6 hash, you can see its value is 3965994044, right? And as you can see, the highest value that is present in our tree is this, which is again smaller than this, right? So it is also mapping to server B. Because to understand that, let us move back to the ring. So I'll just move up. So let's take this example. Let's say here K0 is our server B, which is present here, and let's say our hash is something, the K3 is our server C, let's say, and our key 6 lies somewhere between this K3 and K0. So if you will look into this ring, it will just move to clockwise direction, and it should map to K0, right? It should map to K0, which represents this server B here, right? So now how this is happening, because if we cannot find a hash in our AVL tree for a particular if we cannot find a hash in the AVL tree which is greater than or equal to our keys hash, then we assign it to the leftmost node, which is B itself, the smallest node we have in our tree, because it's a circular. If you will take the image of the ring, it's a circular ring, right? So if the keys hash is the largest among all the hashes present, then it will automatically go to the hash of a server. If it will automatically go to a server whose hash is smallest in the ring, right? Like if you will imagine the ring, this will lie somewhere here, and the next server which will be in the clockwise direction of this particular keys hash will be the server which has smallest hash, right? So whenever we find a key whose hash is greater than all the hashes which is present in our tree, we just assign him to the server whose hash is the smallest, which will be the leftmost node of the tree. And in this case, it's B node, and hence it's assigned to the server B. Now let's try removing a server here. Let's try to remove server C. So if I remove server C from this ring, then you will see the keys that will be redistributed will be only key 1, key 3 and key 4. Other keys will not get affected. So let's try that. So as you can see, only key 1, key 3 and key 4 got remapped, and it's not necessary that they will get mapped to same server. As you can see, key 1 got mapped to B, but key 3 and key 4 got mapped to A. So there is no guarantee that when redistribution happen, it will all go to the same server in case of virtual nodes especially. So this is how consistent hashing works actually. That is all for today's video. Thank you for watching, and please like, share and subscribe.